All right, so we can resume. We have two more talks before lunch. Next one is by Kathy Oliveras from Seattle University. She'll talk about conservation laws and waterways.
Thank you. And thank you all for being here and for the invitation. This workshop's been very productive. And I'm really excited about the talks today, coming later as well, because I'm hoping I could find some applications for what I'm going to talk about in there. So thanks for putting together such a great group. Okay, so I'm going to be talking about conservation laws and the waterway problem. And shortly before the talk, I realized, gosh, my talk is way too long. I'm going to cut out what I don't think is important. And in doing so, I accidentally cut out all the pictures at the beginning that show you what problem I'm actually talking about. So I apologize for that. I'll try to explain what I'm doing with these beautiful figures I've drawn on the board. Okay, the disclaimer, this is a work in progress, so this is actually going to be a rough talk. I've never given this version of it before. Some of it will seem familiar to a few of you, but kind of putting it together in this way, this is the first time I'm doing it, so warning, it's going to be a little rough. It's also, I'm sure that a lot of the things I'm going to talk about have been done or are connected closely to things that have already been done. And so please, you know, if you see anything like that, your comments, your suggestions are welcome and very much appreciated. Specifically, if you see any connections to literature or any potential applications that I'm missing. All right, so what am I interested in general? Well, waves in the real world. So at least I have one figure showing that we have a water wave. Most everything I'm going to do in this talk is going to be one-dimensional, but it's not limited to 1D free surfaces. We can do higher dimensional free surfaces. But I'm interested in waves in the real world, and what applications would benefit from both full dispersion and full nonlinearity. So if you're familiar with the waterway problem, it's hard. I'm thinking inviscid and irrotational even. So the easy of those cases, and still it has plenty of challenges. So I put a few model equations here because one of the questions we see come up over and over again is how important is dispersion in terms of capturing real world phenomena? And so, for example, KDB has dispersion in it. But then, of course, if I modify that by replacing this third derivative term with the full dispersion for the water wave problem, I say full, let me say half of the full dispersion relationship for the water wave problem, generally you'll see better agreement. But the price I pay in bringing all of the dispersion over is now I have to deal with this operator, right? This pseudo differential operator with a symbol that looks like root tang k over k, or in finite depth tang kh, right? I lost the h on the slide. If I want to go to Euler though, and capture the full nonlinearity and the full dispersion, I now end up with this, at least one, there's two equations at the free surface, but one of them is this horribly non-local thing where now I have a differential operator acting on the time rate of change of the free surface, and a different one that looks like an A, but I promise it's a B, okay? And a different operator acting on the tangential velocity at the free surface. Okay, and it's coupled together with this nonlinear equation, the Bernoulli equation at the free surface. But I just want to point out that this operator here, this is, if I took the Fourier transform or the Fourier coefficient of it acting on a function f, well, I have my sort of normal Fourier transform variable, but then I have cosh k eta of x, right? So this is gross. And usually if you want to do expansions or asymptotic formulations, you're going to expand maybe in a small amplitude so that you no longer have this and you can collect like powers and recursively find, for example, a expansion of the Dirichlet-Neumann operator this way. Okay, so my point is that the price you pay for getting better is really, really hard equations. So I'd like to get some better sense of what we can do between these models. Maybe there are better asymptotic models that preserve more of the conserved quantities of water waves when we go to the asymptotic models as well. So just trying to see what more can be done. I also want to figure out what happens on different domains. So normally we think about periodic boundary conditions or decaying at infinity when we're looking at the water wave problem. When we start considering more generic boundary conditions, finding these expansions of these Dirichlet and Neumann operators becomes really challenging. And so I wanted to find a way to do that that made sense to me. That's really the most important thing. That made sense to me, was easy. That's probably second most important, and very systematic. And along the way, out comes conservation laws. Okay, so here's what I'm going to do in what time I have left. So I think I have about 20 minutes. As you can see, I'm not doing great with my 1 minute per slide. I'm off already. So I'm going to go through and develop another formulation of the water wave problem. Now, there's the bulk formulation where we think about it in terms of potential inside a fluid domain, so potential flow inside with nonlinear boundary conditions. Or along the lines of the work of the craft, we can move this to boundary variables and think of this in terms of the evolution of the unknown free surface and the trace of the potential on the surface. So no longer in the bulk, now just at the surface. Or we can think about it in other sort of boundary integral formulations. So I'm going to show yet another one of these different formulations. Using it, we're going to find conservation laws pop out automatically. And then we're going to look at what happens in asymptotic regimes as I look at what happens to those conservation laws as I try to find asymptotic models and can I track those conservation laws without relying on symmetries or other, I'm going to say, complicated machinery that I don't understand. All right, so we are here. So as I mentioned, this is the formulation this is a formulation due to Ablowitz, Fokas, and Muslimani. This is the Bernoulli equation. So this is the trace of the potential on the free surface, is that Q. And you can think about this as a conservation of the momentum type equation. This is, how do I want to say this? Well, I'll come back and say more about that later. This equation here is really the kinematic boundary condition. This is saying that the rate at which the velocity on the free surface, the rate of change of the free surface is governed by the velocity in the direction normal to it. This is where this non-local operators come in, or these non-local operators come in. And you can think of this as an implicit representation of the Dirichlet to Neumann operator. The difference being, if you were to look at formulation due to Craig and Salim, others, you would have A to T equals this Dirichlet to Neumann operator acting on the trace of the potential of the free surface. You can think of this G as somehow being a formal inverse of this operator applied over here. So one of the benefits of this is it's a little bit easier for me to correctly derive the Dirichlet to Neumann operator expansion. Okay, so this isn't another formulation yet. What I'm going to do for this is I'm actually going to convert this dynamic boundary condition, which I call local, because right now it's just defined as an X and T. I'm going to convert that into another non-local relationship. And generally that's going to be for the non-hydrostatic pressure on the boundary of the domain. So you can think about this equation as being in terms of how eta evolves, and the other one will be a geometric constraint on the pressure. Well, for the sake of time and to keep on track with this number here, I'm not going to go through the steps of how these came about. But let me tell you what you are looking at on the screen. So this bar phi, you can think of it just as a test function. This is just any harmonic function that's valid on the domain. Doesn't have to be a solution to the problem. It's just harmonic. And the reason we choose harmonic is so that when you integrate the parts, you don't have that extra boundary contributions. That's really what it's kind of, or that's one way to think about it. Okay, so if I were to take and choose a bar phi that looked like, let's say, e to the minus ikx times the sinh of k times z plus h, then that top equation is exactly this. Okay, so it's just a slight generalization, right? You just use any harmonic function you want. Maybe you choose it so that you don't blow up in k in a certain way. Or maybe you choose it so it's a sort of reordered summation of these kind of terms, right? So that you have better behavior. But that's all I need is harmonic. That local equation, or the dynamic boundary condition, can now be written as this. Where, again, when I'm talking about the contour integral on the domain, or the boundary of the domain, I'm saying you're going around the edge of the fluid. So sides, which may be plus or minus infinity, they might be periodic, they may be fixed walls. The bottom, of course, and then the free surface beta. And so this is just in terms of the potential traced on those boundaries, and the third Pauli matrix, just because it came up. Okay. So for the remainder of this talk, I'm putting everything on the whole line just to make life easier for showing how the conservation laws come up. I also can rewrite those equations by being sneaky. If I assume I'm on the whole line, I'm going to assume that everything goes to 0 at plus or minus infinity. So those boundary or the contributions from the boundary at the sides, those are going to disappear. And all I have left is the top and bottom. And then I can realize I can rewrite these things. And this is where the conservation laws are going to start to come in. Because I can take the time derivative of this test function evaluated on the trace of the surface, and I get it in terms of the potential at the free surface and capital Q, which is going to be the potential at the bottom. Okay. Anytime you see these scripts, imagine replacing Z with eta, or for B, Z with the bottom minus H. The second equation, also I can write this as a time derivative of the product of potential times this interesting quantity. And I can write it in terms of other things. Now, here's the thing. If the right-hand side disappeared, I have conservation laws. I have things that are written in terms of surface variables that are conserved. Okay. So the game is, can I make this disappear? Now, why did I rewrite this way? If you're familiar with the Hamiltonian nature of the water wave problem, this looks like a Legendre type transformation, and that does come up in maybe not this talk, but it is helpful to know. Okay. So again, I mentioned this earlier. I'm going to skip that for now. And so what is the cool thing you can do with this now is you can find additional boundary maps. If you want to relate surface quantities to bottom quantities, you can do that directly and easy. It's easy to find the asymptotic relationships. But here's what I want to think about. What are the impacts of your choice of RP? Remember, that's just a test function. This is like a weak formulation. Really, that's kind of it. Okay. Well, let's search for some conservation laws. Just a quick caveat, when I talk about conservation laws, what I mean is that if I take the time derivative of some quantity at the surface, it can be written in terms of another quantity integrated along the surface, which just so happens to be that if I used a divergence theorem, went back to the bulk, I would find that that was going to end up being divergence free. Whoops, divergence free. Okay, meaning what was a contribution at the top, because the integral, the divergence theorem says the full integral would be 0, means that I can relate this surface integral to quantities at the bottom and sides. Okay. So when I find a conserved density, there may be this sort of flex that has information about what's going on at the bottom and side walls. Okay, a little bit more fun with rewriting those two integral equations, where again, I have this time derivative of things, and I've slightly manipulated them again so that you can see that I have a time derivative of the potential, or this test function at the free surface, and something that I just put in here to make things work a little nicer later on. But you'll notice that this term shows up again here. And that's going to be a sort of recursion that's allowing us to generate this hierarchy of conservation laws. So let's see what happens if we start putting in simple functions, not these functions such as cosh and sinh, but rather harmonic polynomials, meaning things that are like x plus iy or x plus iz to the power. If I just start with the first one and I plug that in, I end up with this integral equation. If I plug this same into the, or if I plug in the square to the second integral equation, I get this relationship here. And if I close my eyes and squint and take real and imaginary parts, then I realize that let's see, the imaginary part of the first one gives me conservation mass. The real part of the second one gives me this conserved density. And then I get conservation of momentum from the imaginary part. And you can keep going. So go up a higher power, plug it into the next equation. And what you see is that as you plug these in, you're getting things in terms of previously computed conserved densities. So you just keep going and you're able to find all of the ones that Benjamin and Oliver found in their paper. Okay, so we're able to generate the same list from Benjamin and Olver, and then subsequent paper by Olver, where Olver proved that these are the only 8 conservation laws for the waterway problem. Let's put an asterisk on that because these are the only 8 local conservation laws of the waterway problem. Okay, so we're able to recover these, but what happens if you keep going to higher powers? Well, you run out of time and patience, and at this point, I haven't really pushed going beyond, but it's an interesting question to see, are there ways you can get at non-local conservation laws using this method? Because there's no reliance on symmetries. There's no reliance on any heavy machinery other than just using harmonic polynomials. Now, of course, there's most likely a very direct relationship. I just don't see it. Okay. What about the asymptotic regimes now? Okay, so what if we want to see, well, how do these conservation laws relate to the conservation laws we know in models such as NLS or KDB or other asymptotic models? And then somehow, if I were to do expansions on Euler, are there directions in which I could get maybe a recursion relationship that closes easily on those conservation laws and generate, I don't know, some interesting integral model? That would be cool. I'm not looking at that right now. I'm just trying to figure out, can I derive NLS and its conservation laws, just as a test to see how this works. Okay, so we have 2 options at this point for how to go with the asymptotic models. We could take those 2 non-local equations we derived and just put the asymptotic scales in there, turn the crank and proceed. The challenge that I personally found is when trying to expand these kind of operators over multiple scales, you have to be very, very, very careful, specifically about what's going to happen with mean values. And it can be very easy to make a mistake when you're trying to let X now be decomposed onto many, many different scales. Now, maybe everyone else is like really good at that, and I know some people are. I just kept messing up and for years trying to figure out how to derive NLS using this, and I could do it in infinite depth, but not in finite depth. The reason why is it all came back to a mean flow issue that I was having when I wasn't careful. So again, we could not modify our starting point and just do the multiple scales expansions there, or we can go back to the beginning, rederive those non-local equations, and then with rederive the non-local equations with those scales embedded, and then it becomes systematic. The price you pay is for every scale you introduce, you go up a dimension in your integrals. But that's okay. There is a singularity, so that, not singularity, but there's a redundancy so that everything collapses at the appropriate order, just like you would hope. Okay, so for example, if I were to introduce multiple spatial scales, so some C, that was epsilon to the j times x minus c j to the t, and I have some time scale as well. When I do that, I am going to basically be able to compose the same type of equation as before. It looks a little bit different, mainly because now these tildes for the gradient are going to be derivatives with respect to each of the scales. These integrals are now nested many integrals, and this should be nested many integrals too. For each scale, I'm integrating over that. And so what are the good choices for the test function then? Well, if you want to get the dynamics, if you want to get the model equations, then choose something that looks like what we had before, where we have e to the minus I k x, where now we have many different k's and many different scales here. And then of course, k times epsilon vector, where this epsilon vector is just 1, epsilon, epsilon squared, epsilon cubed, and so on. So we have this. All right. If I want to do conservation laws, then I'm just going to use those harmonic polynomials. And I'm going to take products of them over the various scales. And then those conservation laws are going to come out appropriately. All right. I'm 2 minutes behind according to my slide count. So let's look at an example. And I mentioned that like I haven't gotten anywhere near the problem I wanted to in terms of asymptotic models. Right now it's just about deriving Binning wrong. So let's imagine though that now I want to find asymptotic models in this regime, where I have maybe something that is decaying at plus and minus infinity on top of something that's maybe periodic, on top of something that is a different scale is moving as a smooth transition. And I want to find what is the appropriate Dirichlet to Neumann operator for that scenario, right? And one that I can efficiently compute, right? And not have to just rely on really, really dense grids and like finite differences. That's going to introduce all sorts of errors. All right, well, we'll start with our problem, by the way. Imagine this is just a Bernoulli constant, because I was trying to do the modulation equations as well, which, by the way, you can with this sort of formulation. But for now, let's put that in as just a constant. And so what we're going to do is make a change of variables. We're going to have theta being x or kx minus omega t. We'll introduce another scale c, which is epsilon x. We'll have our time scale being epsilon t. And then we'll do periodicity in theta and decay in c. And we substitute that in. And this is what the original water wave problem looks like before we move to boundary variables. And if we move to boundary variables, this is what the problem looks like now. This is your Bernoulli equation or the local equation. I did not do the integral formulation because it would not fit. Okay, but this is the local or Bernoulli equation. And then this is that implicit form of the Dirichlet to Neumann operator, where I feel like there may be a small typo. Okay. Don't stare at the equations, get the idea, which is that, yeah, you can rewrite that non-local equation. And notice now that because I have two spatial scales, I have an integral over the period and an integral over plus and minus infinity, because those are the two scales that I put in this problem. This A is just basically a weighted, a weight that goes on to the gradient operator. Okay, things at infinity go to 0 if I want it to be decaying to the same value like this. All right, so I lose the contributions size. And then I now choose my test function because I want to get the dynamics. And so I choose this one appropriately. So notice I have a component in theta, a component in c, and then a component in z, because my test function needs to be harmonic in the domain. And if I proceed to go through, I can expand this or rewrite it. I can plug this in. And by the way, just to make life easy, I've used the dispersion relationship of the water wave problem just to simplify this. Now, if I go back and decide to plug this in to those integral formulations, now I have an epsilon, I can turn the crank, and at each order I get a double integral, but what I'll see is those collapse. And so I can find exactly how the operator should work. I can expand my potential at the free surface and the free surface itself, plug this in, and guys, this is the greatest part. Like you don't have to solve models at each order. This is all done for you. So you put it in Mathematica, you just wait for it to compute. And then you get all the different equations you need to relate. And then you have it solved for your system. And then out comes Mini-Rosk in just a few lines of Mathematica code, which for me was very exciting because this is a finite depth one too, which made me happy because, yeah, that was, it took me a long time to figure that out. So you also get your mean flow correctly for this problem. And this agrees exactly with what you get in the Mini-Rosk paper. And if you want to go to NLS, you just look at how you can combine this mean flow and eliminate the appropriate terms in the equation by introducing another scale and by shifting one of the variables. And so you can derive NLS directly from this as well. Okay, so it works great when you use these cinch type functions to give you your dynamics. Now, what happens if you plug in your harmonic polynomials, you get the conservation laws? Well, you run out of time yet again. And I hoped to be doing this last week, but I ended up spiraling a bit on a different problem, which is good. But it should be systematic at this point to go through and figure out what happens for those conservation laws and to see what happens from there. Where am I headed with this? Well, there's lots of things could possibly do. I'd like to look at the modulation equations, or at least write how you would do the DNO for modulation of finite amplitude waves and let someone who knows what they're doing do something with that. So at least you get the systematic way of capturing the full nonlinearity and dispersion. I'd also like to look at what happens, going back to those conservation laws, what happens in terms of models that are Euler plus dissipation or plus viscosity, and you can find near conservation laws. Or if you want to have generic vorticity, you can find what I'll call irrotational conservation laws plus whatever else stuff you're getting from vorticity. And so these are questions I'd like to ask and explore. I need help, guidance, and suggestions. And so with that, I'm just going to go ahead and stop and thank you for your time. Questions?
For KDV or NLS, we have infinitely many conserved quantities. Would there be any use for the field water?
So this is what I'm hoping is going kind of what I view as the opposite direction, which is from Euler so I have those system and you kind of see that recursion of plugging them back in. On a certain scale, does that recursion close? And are those then related to the type? Because if that recursion closed, that's an infinite list of conservation laws. And would that then be related to these integrable hierarchies of conservation laws? Maybe, maybe not, I don't know. Just because they do seem to come from different types of things, right? These infinite hierarchies for integral models, right? It's kind of these, I don't know what I want to say. All of the ones I showed here come from very specific symmetries of the problem. And so is there a way to kind of capitalize on that? I don't know, but it's something I'd like to play with. And now that I have the asymptotic crank, my hope is, you know, the easy asymptotic crank. My hope is now I can start looking at that.
Just to make sure I understood, so the Benny-Roscus comes out of your model. Did you get to NLS or?
Yeah,
Okay.
so I just had to, at this point, if you just, let's say, move into a different coordinate frame, for maybe I think it's C, if you change this coordinate frame and then combine these equations in the appropriate way, you can eliminate these terms here using the mean flow. And then once you do that, this actually collapses to the finite depth in MS. Yeah. Well, that's it.
Kitty, you mentioned in your conclusions, actually alluded to surprising results on pressure.
Oh,
I don't know if you mentioned it, I missed it.
I copy and paste that slide from an older version of this. But one thing I will say is, if you go back to these, let's see if I can get it here. I think it should be, sorry for going back so much. But if you go back to these integral relations, this is like G eta. This can actually be viewed as a contour integral on the domain in terms of the pressure on the boundary. And so what you can do is if you write it in terms of those, or actually here, this is a better way to see it. This can be related to the pressure at the bottom, the time dependent pressure. So you can get direct maps between surface quantities and the time dependent pressure at the bottom. And with that, one of the things I've been doing is now I can do a time series problem, try to eliminate the spatial component, which in the appropriate sort of asymptotic regime you can. And then put in a Leuenberger observer to kind of see if you can take the time series data and reconstruct the surface. And it seems to work, but it's all because you have that direct map there. But I think there's more to be exploited, like in terms of, I had not thought about this. Now I feel like an idiot. Maybe I can write this in terms of the normal of the pressure. And look more in terms of the case of constant vorticity, which I can do like this. I never thought about that. Sorry, that's related to a different problem, but that was the one I was spiraling out of control on last week. Yes.